regression is really, really flexible. Anything that you can do with a t-test, you can do with regression. Anything that you can do with ANOVA, you can do with regression. So some people really prefer using regression over t-tests or ANOVAs for that reason. I like t-tests and ANOVAs because I like working with factors, things that I manipulate, and I have separate conditions for each. But regression can be really, really flexible. So on the homework, there were questions about your test scores, right? So your test 1 and test 2 scores. And I asked you, like, what was the correlation between test 1 and test 2 scores? And you found out whatever it was. I think it was 0.66 something. And I said that it was highly significant. At the end, excuse me, at the end of the class today, we'll see how we can determine that this is statistically significant. But the question that we were asking, like with the homework, are test 1 scores related to test 2 scores, right? This can be useful. You might wonder if, like when you are designing a class, like how many tests do you need? If you can accurately predict how people do based on one test, then maybe you don't need to have any more homework assignments or anything, right? But the relationship between test 1 scores and test 2 scores wasn't perfect. Why do you think that is? Why wouldn't the correlation between test 1 scores and test 2 scores be perfect? There are what?
Many reasons.
Many reasons. For example, what?
People slept for the first exam. They didn't sleep enough for the second test.
People slept for the first exam?
They slept enough before the first exam. They didn't have much sleep.
So maybe some people that got a lot of sleep for the first exam didn't get much sleep for the second exam. Maybe. What else?
They didn't study hard.
Maybe some people studied harder for the first exam than the second. They thought, oh, the first exam wasn't too hard, so I don't need to study as hard for the second. Or maybe it's the opposite. They're like, oh my goodness, that was hard, so I better test, or I better study more for the second exam. So we didn't have a perfect relationship. Anyway, if we plotted the test 1 and test 2 scores, if you did the scatter plot, you should have saw something like this. And in general, it looks like what's happening? Is there a relationship between the two? What's the relationship? There's a positive relationship, meaning that as test 1 scores increase, test 2 scores tend to increase, right? So we found a positive correlation, 0.67 if you round. So higher scores on test 1 are associated with higher scores on test 2. Now, let's say that we want to describe this relationship between test 1 and test 2 scores, more than just a correlation. What could we do? Well, let's start with the things that we already know. If we ignore test 1 scores, what's our best estimate of someone's test 2 score? The mean of test 2 scores, right. So the mean of test 2 scores, this is our best estimate of test 2 scores if we don't account for the linear relationship between the two. And this happened to be 70.3, which is rounded. Okay. If we ignore the test 2 scores, what's our best estimate of our test 1 scores? The mean of test 1, right? And this is rounded 76.9. So if we replot the scatter plot, so these are our data, we can create a point that describes our best estimates of both scores, right? So it will reflect the mean of test 1 scores and the mean of test 2 scores. If we do that, there it is. So notice that this is sort of like in the center. We have more scores over here, which is why it's not over this way a little bit more, right? So it's centered around X, and it's also centered around Y. So this point is our best estimates of our test 1 and our test 2 scores if we don't take into account the fact that there is a linear relationship between the two. So we said that those are our best estimates. What does it mean when we have a best estimate?
Unbiased.
Unbiased estimate, that's good. So a best estimate, maybe in some senses, should be unbiased. Okay, what?
We can make t-tests.
We can make t-tests with means, that's true. What else does it mean?
Average.
The means are a type of average. Oh man. Do I have 5 lyrics? No, I don't. Oh, sorry. So no lyrics for anybody today. It's not giving away 20 lyrics. All right. Think about when we were computing standard deviations and variance and things. And what we were doing was we were finding the difference between each score and mean, right? And what was the property of the sum of the differences around the mean? So the differences around the mean, each difference was an error, right? We have a difference for one person, a difference for another person. When we sum all of those differences together, they balance each other out, right? This is why we like the mean over, let's say, the median. Because when we use the sample mean, we have a value that all of the errors, all of the deviations or differences are completely balanced. They're perfectly balanced. So best estimates, one thing that it means when we have a best estimate is that all of the deviations around the means sum to 0. So if we did this, so T1, so each score that we have for test 1 minus the mean of test 1, if we sum those up, we got this, which is basically 0, right? You put 13 zeros in front of this. Okay, we do the same thing for our test 2 scores. The differences are the errors. So for each test 2 score, subtract the mean from it and add up all of those errors or all of those differences. We also had something that is basically 0. So these meet our definition of a best estimate. There's one other thing. Do we use the sum of the deviations?
No.
Are there some of the errors? We don't. What do we use instead? We take the square of those differences, right? Instead of just summing up the differences, we sum up the square differences. So, oh, sorry, I guess I'm jumping ahead of myself. If we were to use a different value instead of the mean here, so if we were going to subtract some value from every T1 score, so let's say we did sum of T1 minus the mean, so this is the same as the first part, plus 0.5. If we take this sum, we get negative 21.5.
Why did we get
To demonstrate that the deviations around the mean sum to 0, but the deviations for other values, if we get the deviation from T1 and this other value, it doesn't add up to 0. Okay? If instead of adding 0.5 we subtract 0.5, we get the opposite sign version of that. Anyway, okay, so we have 0, sums of zeros for up here, sums of not 0 there. Another property of a best estimate is that the sum of the squared errors, sums of squares, is going to be as small as possible. So it will be minimalized. If you watch some videos on YouTube or Khan Academy, you may notice people talking about least squares. Least squares. So the least squares means the smallest sum of squares that you could potentially have. So let's figure out what our sum of squares are. So we take the sum, each score from test 1 minus the mean of test 1. That's the error, the difference that we calculated before. Now all we're doing is square errors. So when we do that, we sum everything up. 7,850, basically. If we do this for our test 2, we have the sum of our errors, or our differences, squared, and that's 8,287. These are minimal. Let's demonstrate this just for the test 1 again by picking some other value. So before we added 0.5, right, to the mean, and we found that the sum of those errors was equal to negative 21 point something. If we square each of those errors, we get something like this. 7,860.4. Now what's the relationship between this and this?
Greater.
This one is greater than this one. It's not greater by much here, but it is greater. So if we did basically the same thing that we did on the last slide, and instead of adding, we subtract, what do you think the value will be?
Smaller.
The same. He says it will be the same. It is exactly the same. Because the sign here, since we are squaring those, that sign goes away, right? So we have for another value, where each value is just 0.5 above, or another value where each value is just 0.5 below, we get a sum of squares that is slightly bigger. So you can do this for yourself with R and test different values. Add 0.1, add 2, add whatever. And you'll see that any time where you have anything except for the mean here, that these sums of squares are going to be bigger than the sum of squares around the mean. Which means that this sum of squares is the smallest sum of squares, or the least squares that we can have. Okay. Now, when we were doing t-tests and ANOVAs, we often weren't satisfied with the single best estimate, right? We had 2 samples for a 2-sample t-test. And how many estimates did we have for our 2-sample t-test? We had 2, right? We had the mean of sample 1 and the mean of sample 2. If we did an ANOVA with 2 factors, with 2 levels for one factor and 3 levels for another factor, we ended up having 6 different conditions, right? So we created best estimates for each level of our different factors, or for each combination of levels, or each condition of the factors, right? So what we need to do here is something similar. Now, we haven't grouped things into like high test 1 scores and low test 1 scores, right? We could do that, and then we could do a regular old t-test or an ANOVA. Instead, we're just working with test 1 scores and test 2 scores, but there's a linear relationship between them, right? We have a correlation. I said it was significant, and we'll see later that it is. So, what could we potentially do? Is there any way that we could create estimates for test 2 scores from test 1 scores?
If we have the correlation, the value of the correlation.
Okay, if we have the correlation, we do.
And we just can interpret this value, so we can calculate the second mean.
Okay, so how do we do that? If you know the first mean and you have the correlation, how do you calculate the second mean? Or how do you estimate the second mean? This is what we want to do. We want to get estimates. So for each test 1 score, we want to estimate what the test 2 score should be. Does that make sense?
Bigger than the relationship. Can you say that? Can we guess that it should be bigger than what we have as an interaction?
I'm not sure. What do you mean by interaction?
I mean the relationship. For sample 1 and sample 2, they like if we say they are real tests, and we got the relationship, and we can say it should be bigger than what we have.
I apologize, I didn't understand what you said. Sorry.
So we have this, for example, the mean for exam, the first test is 76.
Okay, so we have a mean for the first exam.
And we have 6 point something for the correlation.
We have 6.6 something for the correlation.
Even we multiply by something and divide, or it's like there is something we should do.
There's something we should do. We should multiply by something, maybe divide by something. Okay, maybe. We will end up multiplying and dividing by things, so you are right. Okay, so with correlations, we have variables that are linearly related, right? This means that we should be able to create a function, some linear function, that we can predict y, or predict our dependent variable from the independent variable. We should be able to predict someone's test 2 scores based on their test 1 scores. Now, if we only use the means as estimates, then we don't capture the linear relationship. What we need is a best estimate for our dependent variable, that is our test 2 scores, that captures this linear relationship. So if we want to capture a linear relationship, let's make a line. It's easy. So making a line is easy. Making a line that fits the data best, maybe not so easy. We want the deviations around that line to sum to 0. And what else do we want? So a best estimate has the property that the sum of deviations or the sum of errors equals 0, and the sum of the squares is minimal. So it meets that least squares criterion. Okay, so what's the function for a line?
The slope and the intercept.
It has something to do with the slope and the intercept, yes. Y equals
some value x plus minus
some value times x plus some value, right? So we have y equals some value times x plus some value. So what are these different pieces? So m is the slope.
Y is the independent.
Y is the dependent variable.
X is independent.
The independent variable. And the intercept, right. So y is the dependent variable, m is the slope, x is the independent variable, and b is the intercept. So what we need to do is find a slope and an intercept that best estimates y from x, or in terms of test scores, that best estimates test 2 scores from test 1 scores, right? Okay. So let's start with the slope. What is a slope? What does it mean if you have something with a slope? It's y divided by x. It's not just y divided by x.
And
minus
b minus y divided by
Minus y divided by?
y minus b divided by x.
All right, so we had some person saying it's y divided by x. Someone else said it's y minus b over x. Those are both wrong. All right.
Minus y.
minus
Minus y minus b.
Minus y divided by x, it's also wrong.
Minus y minus b divided by x.
Minus y minus b divided by x.
Or minus y minus b.
If I say that the slope of something is 2, what does that mean?
That when x is 1, y is
M equals 2. Okay, well, what does that mean if m equals 2?
when y is 1, x is 2.
That is
So we don't know what the intercept is yet, so we can't say anything like that. X divided by 1. X divided by y. No. Some of you guys may have seen something like this. Delta y over delta x. That is correct. That will give you the slope. Delta y. What is delta y?
Delta is for
different.
Delta y is a difference in y's. And delta x is a difference in x's. Or changes in y's over changes in x's, right? If you had 2 values of y and 2 values of x, you could do something like y1 minus y2 over x1 minus x2, right? You can do something like that. Then you have a change. So for some difference in x, there's also some difference in y. So a slope of 2 means that for every 1 that we increase in x, we go up 2 in y, right? So the slope indicates the changes in y over the changes in x. They also refer to this as the rise over the run, the rise over the run. All right. So the question now is, do we have any measure that indicates changes in y or changes in x?
Two test scores.
We have what?
Two test scores. Any test scores.
We could take any two test scores. We could take any two test scores.
Or someone's two test scores. Just
Someone's two test scores.
Two interaction. Two.
So let's do this. Now, the great thing about two test scores is that any 2 points describe a line, right? And we can figure out the slope exactly. Come on, where is it? Okay, so let's take this test score and this test score. So we have a slope like this, right? Let's take this test score and this test score. Uh-oh, we have a slope like that. Let's take this test score and this test score. Oh, we have a slope like that. So we could take different test scores, but we're going to be coming up with different slopes, right?
So we take as, for example, the mean,
Okay.
the highest and the lowest two test scores. Then, I mean, we can make a triangle with the third line of the plane.
So we can take the highest and the lowest of the two test scores. So this is the highest and the lowest of our test 1 scores. And this is our highest and our lowest of the test 2 scores. And so then we're going to draw a triangle
For the mean.
from the mean. I'm not sure which triangle we would draw. Maybe. One thing that we could potentially do is we could find the slopes for all of the combinations of the points and maybe average them or do something else like that. But there's something actually much easier. So, we want something that tells us about changes in x.
Variance.
Variance tells us about changes in x, right? It tells us about how x changes over all of the x's, right? So, in addition to variance, we also have standard deviations. Now let's think about what the variance and the standard deviations actually tell us about. So the variance actually tells us about changes in x squared, or in y squared, right? We have squared differences, squared changes, right? So it tells us the average squared change in x. But we don't want a squared change, we just want a change, right? Because the formula isn't the changes in y squared over the changes in x squared. It's the changes in y over the changes in x. So we can take the square root of our variances, right? So that will give us changes in y or x. So if we do this, we can have something like this. So our first attempt at figuring out what the slope is. And he is shaking his head. No, he doesn't like this. Why don't you like this?
It's confusing.
It's confusing. How is it confusing?
Because we have the standard error, and this is the same sign.
So we have the standard error and this is the same sign? What?
One by standard deviation, and it's the same sign. So is it the same standard deviation, the bias?
Yes, if we squared this, oh, look at that beautiful black. If we squared this, that's our unbiased variance estimate for y, right? So this is the standard deviation based on the unbiased variance, which tells us something like, on average, how much y changes, what the average change is, right? So we're taking something that is indicating like the standard, standard deviation, standard change. The standard change in y, dividing it by the standard change in x. Now, interestingly, you said something about the unbiased versus the biased. It actually doesn't matter here, whether you use the biased or unbiased. Can anyone tell me why?
Can you ask me?
So what I said is that it doesn't matter whether you use the biased or unbiased forms of the standard deviations. I have the unbiased ones up here. It doesn't matter if you use the biased or unbiased.
Because ratio will be same.
The ratio will be the same.
Ratio between unbiased variance of y and x will be equal to biased variance.
Yes, the ratio is going to be the same. So the unbiased version, we were dividing by n minus 1. We had n minus 1 in the top and the bottom. If we use the biased versions, we're dividing by n. We have an n in the top and the bottom. So it doesn't really matter which form you use. I like to use the unbiased forms because R, you can say SDT1 and get the unbiased standard deviation. All right, so let's try to figure out what the slope is. So if we do this, we're taking the standard deviation of test 2 is our y, divided by the standard deviation of test 1, and we got 1.03. So the ratio between those two is 1.03. So if that's the slope, what it means is as someone's score increases 1 point on test 1, their test 2 score should increase by 1.03 points, right? So if we were to plot the original data again and plot a line that ignores the intercept for the moment and just uses the slope and x to predict our y values, we get something that looks like this. How does that look? It's positive. Well, that's good because we have a positive correlation. So we should have something that's positive. Good, okay. So that's all right.
Over the mean.
What's over the mean? So this line doesn't actually pass through our best estimates. Ooh. Our best estimates without accounting for the linear relationship. They have, okay, so there's a deviation for one score, or error for one score. Here are the errors for all of our scores. So if this line actually gives us our best estimation, what should happen?
There's a difference sum to close to 0.
Yeah, if we add up all of these differences, right? These are positive differences, these are negative differences. If that really gives us a best estimate, then all of those things summed up should equal 0.
And the squares should be minimal.
And the squares of all of these things should be minimal. All right. So, let me show the graph. All right, so if our estimations are best, those should sum to 0 and give us the least, or the smallest least squares possible. It's sort of redundant, sorry. Just the least squares possible. All right, is it best? Well, let's figure this out. First, we need to figure out what the errors are. This actually isn't that complicated. All we need to do is take each test 2 score and subtract the estimations that we have for the test 2 score, right? So T2 minus our estimation of T2, that will give us our errors. So those will be errors. If we sum up the errors, what do you think we'll get?
Equal
It's basically 0, rounding error. Yeah. So this, we're looking good so far. Off to a good start. Now, the sum of squares, what's that? How could we figure out the sum of squares? So this was the sum of our errors. How could we find the sum of our squared errors?
errors.
Yeah, all we have to do is just say sum errors squared. Boom, we've got it. And it's 4,566. and change.
How can we know that it's the minimum?
How can we know that it's the minimal? Well, you could do some very complicated mathematics and actually prove it, or I don't know why I use the quotes for that, because in math you can prove things. So you could prove this. We're not going to, because the math is fairly difficult. So we're going to try a couple different slopes and intercepts and see what happens if we get bigger sums of squares or smaller sums of squares. And if you want, you can practice with hundreds and hundreds of other slopes and intercepts if you're really up to the challenge. Okay, so the question is that the least that the squares could be? Let's find out. So I said this was our best estimation. We have the sum of the errors and the sum of the squared errors there. That was a line that went through it. This was our first attempt at what the slope was. Right? We came up with the 1.03. So that line, if we were to make predictions on that line, then the prediction for this would be here, the prediction for that would be here, prediction for this would be there. We do the same things. We could find those predictions, find those estimations, and subtract them from the actual scores that we observed, right? If we do this, our sum of errors turns out to be greater than 0, less than 0. What do you guys think?
Less than.
Actually, it turns out to be less than 0. Why?
Because there are so much figures below the.
Yeah, most of these values fall beneath this line, right? So we only have a couple positive errors, and we have a lot of negative errors, right? Importantly, though, that is not 0. It's not 0. They don't sum up to 0, and it doesn't look like rounding had any, result in this not being minimally close to 0. So what do you think the sum of squared errors will be? Greater than that. Let's see. 4,566 is less than 8,683. Turns out this sum of squares is bigger. All right. Now earlier when I drew this one, someone said that we shouldn't draw this. We should adjust, right? We should make this go through this, like that. Use the same slope, but change the intercept to make it go through there. So we can do that. Oh, wow. So, here we're using that original slope that we found, the 1.03, and then we found the intercept. How did I find the intercept for that?
Why understanding?
I did basically the same thing that I did before. So y, or the mean of y, minus the slope times x. So I found the intercept. Here's the form for this equation. We can then see how much our predictions are off. So that would go down to there probably. Right, so these are our errors. What do you guys think the sum of errors is going to be? Still negative.
But more close to 0.
More close to 0? This is actually kind of cool.
It's almost 0.
It's basically 0. Why?
Because that's the mean.
It goes through the mean, which is the best estimate that we have. So if it's going through that, the means balance out the errors, right? So this formula, by going through the means, it's doing something equivalent to balancing out the errors. Think about if we had a line like this, right? Well, this is just y equals the mean of y. And the sum of the differences between y, each y squared, and the mean of y, that's 0, right? Cool. Well, so, wow. This looks exciting. Maybe we have something that will be a better fit than what we had before. What do you guys think the sum of squared errors is going to be? Greater. note, the errors are minimized here. The sum of the errors is 0. When we sum up the square errors, we got something bigger here than we did here. This actually is our least squares estimate. Okay, that's best. Let's think about our dependent variable. So we can express our y-squares. It's basically the estimations that we have plus some errors, right? So we had some points, right? And we said, okay, our estimates are here, 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 and wherever, but the actual data were here. So each one of these points is really just the estimate plus some error, right? And the error for these different ones is going to be different. Why? Because some people slept in late, some people studied harder, some people did more homework, right? But basically, that error is going to be independent from the estimates. Remember earlier when we were doing ANOVAs and we broke variance up into pieces, into independent pieces. We said, okay, this piece is independent of that, and this goes for this, and this one goes for this, and this we're going to be using for the error. So we can think about our dependent variable in the same type of way with regression. So our estimates of y and the error are independent. So what should happen? The variances should sum. Should be able to add them up. More than that, it should sum to equal the variance of this, right? If both of these are independent, very independently of one another, then this variance should equal that variance plus that variance. Like we were doing before, the total variance is equal to this, and we're going to break that into variance for some effect and some variance for error, right? So, we can do variance of our test 2 scores, turns out to be almost 200. The variance of our test 2 estimates, what do you guys think? Is this going to be bigger than or smaller than?
Smaller.
Smaller than. It doesn't spread out as much, right? It all fits on that line nicely. That's about 88 and change. And our variance of our error. What do you guys think that that's going to be? If you subtract the 2, so when I calculated it was 108. Is that about right?
Yeah.
Well, if you do the math, 108, if you add up these things, or if you subtract these things, you will get the other piece. So this actually works. So the variance in the observed y's, we could break down into pieces. Pieces that, or not pieces, a piece that is due to our line, to our estimations, to our best estimations, and a piece that's due to the error. Now, when we've been doing like tests, typically we have something that's like the variance of the effect on the top, right? So for our f-test, we had the mean squares of the effect over the error variance. For our t-test, we had like maybe a difference between means, which is something like the variance between the means, over standard error of the means, right? Which was variance in the sampling distribution of the means. So we have these different pieces of variance. I mean, that's the question, what percent of the variance in our DV in test 2 does our best model explain? So this would look like this. So this is the variation that our model explains over the total variation, right? So if we do this, we get that. What do I mean by percent? So this is not expressed by a percent, but I could write it as one. How would I write this as a percent? 44.9, sorry, 0.9 or whatever percent, right? So what this is saying is that 44.9% of the variations, of the variance in our dependent variable is explained by our estimate. Now this is neat. Watch this. So the correlation between T1 and T2, R, was 0.670101 jets. If we square that, what do we get?
Okay, it's the same, but
It's the same thing. Those are the same thing. Whoa. Dude. So, R was this index telling us something about the strength and the direction of the relationship between two variables, right? It's not a percentage, because it goes from like -1 to +1, right? So like the percentage goes from 0 to 100, right? If we square R, what we get is the percent of variance in the dependent variable that our model, our best linear model, explains. That's kind of cool. This is called the coefficient of determination. Coefficient of determination. What? So R squared is the percent of variance in our dv that is determined. Thus, the determination part of the coefficient of determination. So we have a lot of variance in our test 2 scores. And 44.9% of those variations are determined by the linear relationship between those two variables. If, on the other hand, we do 1 minus the coefficient of determination, what should we get? If the coefficient of determination is the percent of variance in our dependent variable that the linear relationship explains, what would 1 minus R be? Yeah, so 1 minus R squared is going to be what's left over. It's the percent of variance in our dependent variable that the linear relationship does not explain, right? Or the percent that's explained by errors. All right, so let's talk about hypothesis testing. So, I was struggling with this one. There are a number of different ways that you can hypothesis test for regression. Before, when we were talking about hypothesis testing, we drew like sampling distributions of the means, or sampling distributions of variance. Well, we can create sampling distributions for R. So sampling distributions for R, the name for it is, I'm going to mess it up, the bivariate normal distribution. So before we had a normal distribution, right? Bivariate. What does bivariate mean? Bi means, let's go bi-cycling. What is a bicycle? Two. Bi means two. Bivariate. Two variables that are each normally distributed. So if the population, so if rho is equal to 0, you will get something that looks sort of like that, where this is -1 and this is +1. As you move away from 0, you will get different shapes. So this would be for a positive correlation. If you had a perfect correlation, you would just have, if the population was perfectly correlated, then every sample you would get would also be perfectly correlated, right? But basically what's happening is that the bigger the correlations get, the more skewed these are getting. And similarly, if you have negative correlations, you observe skew in sort of the opposite direction. Now, R by itself doesn't have the capability to do hypothesis testing with those types of distributions. There's some things that you can add in to allow it to do that, but we're going to do some things that will allow us to use the stuff that R already has in it. So, turns out, if you do a transformation, what is a transformation? You add something, you subtract something, you divide or multiply. You basically do some manipulation to some variable. If you do the right type of manipulation, you'll have something that's approximately distributed as an F. We aren't going to use that. Instead, we're going to use another transform, and we're going to get something that's distributed as a T. We're going to use this one. All right, so if we take another look at our t-test. So back before when we were doing t-tests for like one sample mean, we had something like this. T is going to be equal to the mean of x that we observed minus the population mean, the hypothesized population mean, right? And then we were dividing that by some standard error. So, we have our observed value, we have a hypothesized value, and we have some standard error. And the standard error was like a square root of error variance, right? We were calculating variance, and then we were dividing by the degrees of freedom, right? So we had things that looked like this, right? Where if you were to also square this, then you could put the whole thing underneath the square root. So we had something that was like some square root of error variance. This was the variance of the sampling distribution of means, or the sampling distribution of the difference between means, or whatever sampling distribution that you were dealing with. But basically what we had was an observed value minus a hypothesized value divided by some error variance that was divided by some degrees of freedom where that was all taking the square root. So if we do the same thing with our correlation, we have something like this. So R, this is the R, the correlation coefficient that we actually observed. For right now, we're going to stick with all hypotheses of no difference, right? There's zero, there's no linear relationship. Over what? Well, so we have the square root in the bottom. What's that top part? 1 minus r squared.
Variance.
This, remember r squared, this was the percent of variance in the dependent variable that was accounted for by the linear relationship, whereas 1 minus that, this was the percent of error variance, right? The percent of the variance in y that wasn't determined by the linear relationship. So that's like error variance. It's like the same type of thing that we were doing before. And this n minus 2. N minus 2. Why do we have n minus 2? Why don't we have n minus 1? We have 2 samples, which means we have 2 means. 2 means that we're estimating, right? We're getting standard deviation of x, where we use the mean of x, and we're getting a standard deviation of y, where we're getting the mean of y. So we have 2 means. So we're losing. Yes.
Standard error. We
Yes.
didn't have n minus 1. We're supposed to have n.
Oh, yeah, you're right. So the standard, so we had we had something like this over n minus 1, right? And then we took the whole thing over the square root of n. Like that. Yeah. Let's ignore that for the time. This turns out to be the correct way to calculate the t. You can imagine putting the square root of n in the bottom, but that won't give us the right answer, so I conveniently ignored that for Okay, anyway. So, if we do this, our null hypothesis is that the population correlation is 0. We'll use a traditional alpha. There's our formula. We can solve for it. So we have the correlation between the two. That was 0.67. We have n, the length. So that was 43. So our t-value, this is r. The square root of 1 minus r squared divided by n minus 2. And we get 5.78. What do you guys think? Is that going to be significant? We can figure out the critical value for t if we wanted to. How would we do that? We can say t crit equals qt 1 minus alpha. It's not 1 minus alpha.
Divided by
Divided by 2 because we have a two-tailed hypothesis, okay? And then degrees of freedom, n minus 2. Cool. We could do that. I just went and I found the p-value using pt. So 2 times 1 minus pt, the cumulative probability of observing this, given those degrees of freedoms, turns out to be pretty small. Much smaller than 0.05. What do we do? We reject it all. Try it. Cool. That's it. So now you know how to take the correlation and using the correlation and the means that you have for each of the samples, you can now calculate what the slope should be for the line that will test it. You should be able to calculate what the intercept will be. And you can now calculate whether or not that correlation actually is significant. So for the homework tonight, we're going to be working with the same data set that we did last time, that is your test scores and your homework scores and the number of times you've submitted homework. And we'll see how much increase in test 2 scores people got for turning in one more homework assignment. Stuff like that. Finding the p-values for the correlation. Fun stuff.